Thank you, and very good afternoon to you. My name is Arun Gupta. I work for Amazon, and today I'm here with my colleague, Adrian Hornsby, who'll be joining us a bit later. We both work at Amazon. This talk is about serverless architecture patterns and best practices. With serverless, there are as many architecture patterns as many their customers are. What we're going to show you today is some of those patterns that we have seen within our customers. There are a variety of ways by which you can talk to us, email, Twitter, or GitHub handles. In the lay of the land, the way we are looking at it is we'll talk about serverless key concepts, Lambda basics, talk about some of the basic concepts over there. We'll also talk about serverless application model, how you can easily deploy your serverless applications as opposed to just one Lambda function. We'll talk about how you can build your CI/CD deployment pipelines very easily. We'll talk about application monitoring in terms of Lambda context, event processing, and then eventually conclude with real-time streaming use cases for Lambda. Let's talk about the concepts. Now, I know there have been a few serverless talks today, so I'll just cover through the basics quickly and then jump into the real meat as well. AWS has this concept of a region, which is a geographical location where data centers, a cluster of data centers are being built. Each cluster is called as an availability zone. Now, with serverless, one of the key concepts is availability, a high availability of your service. The idea is, by default, if you are looking at a serverless, then that server, there are no servers to manage essentially, but that service or the function is highly available. That means even if an availability region or availability zone goes down, your function will still be available. Another important aspect of a serverless is the ability to able to raise or to scale with the usage. So today, you maybe built a fun application for your own hobby, and if that application takes off, then you have the ability to grow the application along with your application usability. So for example, today you're launching it in a particular geographical region, but now your application needs to go global and to be deployed across multiple regions and availability zones. That can be done very easily as well. Of course, one of the key tenets of serverless is you don't pay for the storage of the function itself. You only pay for the compute capability of the function itself. Let's take a look at a spectrum of AWS offerings in here. Now, there is EC2, which is a classic EC2 service. On EC2, for example, you can deploy your own Kafka or Docker or Cassandra databases very easily. But if you were to configure them in a highly available manner, essentially, you will have to deploy them across multiple availability zones by yourself, or across multiple regions, again, by yourself. That option is certainly there. If you take a look at a managed set of offerings that we have, Redshift or Amazon RDS. Now, you're getting a MySQL-compatible database where you have an option to automatically be available across multiple availability zones. So Amazon has done the hard work for you. You just need to check the option, and it will be available across multiple availability zones for you. And then comes serverless, essentially, which is on the far right here, essentially, what we are saying is, which is by default available to you across multiple availability zones. There is no hard work you need to do. As a developer, your focus is on writing apps. Let Amazon do the undifferentiated heavy lifting for you, where you can focus on to build the apps, and the service is automatically available to you. Now, one of the first services that was, or the first service that was launched as part of AWS was S3. And Lambda, or serverless, if you think about it, the whole concept of serverless is highly available across a region, across multiple availability zones. The second service that was launched for AWS was SQS. So right from the genesis of AWS itself, if you think about it, we have been creating that serverless paradigm. Now, the people, typically developers, most associate serverless with AWS Lambda. Now, that is, again, created based upon customer feedback. So at AWS, 90 to 95% of our roadmap is driven by customers. And so AWS Lambda was created as a request to our customers because they wanted to add some compute capability to S3. So we created AWS Lambda. Now, expanding the landscape from there, now S3 is an event to Lambda, but then our customers add more triggers or events to Lambda. So then we started kind of expanding the horizon over there, and now a lot more capabilities are available, a lot more triggers or events are available which can trigger an AWS Lambda function, essentially. So let's take a look at some of the Lambda basics here. There are a variety of languages that are supported. So of course, Node, Java, Python, C#. Those were sort of the first set of languages that were supported. Customers have been using Go before we officially supported Go. That's one of the beauties of Lambda itself. And I mean, there have been tests where they've been able to run Fortran language by bringing their own binaries, so the extensible nature of AWS Lambda itself. There's a simple resource model which acts like a power button. From your side, you just need to choose a memory setting ranging from 128 megabytes to all the way up to 3 gigabytes. You choose a memory setting, network and memory is allocated to appropriately. So you just change the dial, and the resources are allocated to you accordingly. There is also different usages on how you can create Lambda functions or invoke them. There is a synchronous usage, there's an asynchronous usage, and there's a streaming usage of it. Let's take a look at that next. In terms of synchronous, you call a Lambda function, and the Lambda function responds back to you. You wait until the Lambda function responds back to you. A typical usage of that is where you are front-ending a Lambda function with an API gateway. So you have a REST API, you call the REST API, an event is triggered that calls the Lambda function, comes back to the API gateway, and you receive a response back. That's a synchronous response. Now, there is an asynchronous response. You have a S3 bucket, a document is uploaded in the S3 bucket, or you have a SQS, an event occurs in SQS, and you want to get a response back, or SNS rather. A notification happens, you want to trigger a Lambda function on that. So that's the asynchronous model, because somebody else is uploading a document in S3, and your Lambda function is triggering. And we'll talk about some of the use cases of that, how our customers are using it. And then last but not the least, there's a stream-based use case for the Lambda execution model. Think of it like a Amazon Kinesis or DynamoDB streams. So now in DynamoDB, for example, a row gets updated, and another row gets updated, and another row gets updated. So that's like a stream of updates that is coming to you. The important part to understand that in DynamoDB stream or stream-based model is the order is very important. That's not the case in asynchronous modeling. Let's take a look at how a Lambda function looks like. And I'm using a Java code here, basically. But there are essentially 3 parts to a Lambda function. The first of all is a handler function. So in Java language, you need to implement a particular interface, which is well-defined. And as part of that interface, what you get is a handler function. There is a method called as handle request in this case. Now, in handle request, that's the method name. There are 2 parameters. The first parameter is your payload that is coming into the function. So if you invoke using an API gateway, think about a JSON payload going to API gateway, then getting translated to the Lambda payload, and then you receive that as a POJO, in your case, as a book object. Second object is, or the second parameter is context, which is sort of the runtime context, which provides a lot more about the execution ID, the timestamp, and the runtime context of the Lambda function itself. And you can leverage that multiple ways in your function itself. Let's talk about Lambda best practices now on that, what we have seen, how our customers are using it. The first practice is how you should separate the Lambda handler from the core logic itself. Now, in this case, for example, if you take a look at it, I have the method called as handle request. There is a book payload that is coming in, and then I have a runtime context. Now, the idea in this case is I want to save the book. Every time I'm getting a request, I want to save a book into the database. And in my case, I'm using a DynamoDB as a backend. So the handle request method is called for every invocation of the Lambda function. Now, if I'm doing my database initialization over there, then the function becomes expensive. For every invocation, I'm invoking, doing the database initialization and storing the book in there. So what I'm doing in this case is, first of all, I'm extracting the database initialization outside the handle request. So it's a static initializer, so it gets called for the first invocation of the function. And you need to also think about it. This is a JVM-based function, so it takes a few seconds for the first invocation to warm up the JVM. But then, once it is warmed up, you can also set the concurrency context, or how many times the concurrent execution of the function needs to happen. The maximum limit for that is 1,000. So essentially, if you can invoke the function 1,000 times concurrently, the database, in your case, is initialized once, but the handle request method is called multiple times. So there are ways by which you need to optimize on where you should put your database initialization, cache initialization, et cetera, outside the handle request method. The other benefit over here is now, because my save book method is outside the handle request method, it improves the testability of my code. I can unit test the function very easily, as opposed to calling the handle request method and creating how my payload should look like. So this is sort of the key message that I wanted to convey here. You create a zip bundle for your Lambda function. That zip bundle gets uploaded to AWS Lambda, and it gets expanded over there. Well, first of all, there are runtime limits. There are limits in terms of how big the bundle can be. Then there are limits about how big the expanded bundle could look like. So yes, it is very tempting to, in your Maven file, for example, when you're packaging your function, to just use the AWS SDK and say, you know what, build in all the dependencies. But what you need to do is, you really need to be very selective about what dependencies need to bake in. So in my case, for example, I just want to build the AWS Lambda Java core. That is one dependency that I care about. And then the other one I care about is only DynamoDB. AWS Java SDK has a lot of dependencies. I don't care about all of those dependencies for this particular use case, so I'm just narrowing it down to a specific version. Now, in the Lambda runtime, we provide support for AWS SDK, but I may need a specific version. So it's very important that you nail it down to the exact version, because we don't want your application to break if we change the runtime dependencies in the Lambda runtime. So bake your dependencies into your application and be very selective about what you need to bake in there. EC2 has a metadata API, which provides a lot of details about what is sort of the execution context of an application, or about the EC2 instance that is being provisioned. Now, as part of the metadata API, there are lots of environment variables that are exposed to you. So in this case, for example, AWS region, or which availability zone is where you are running it, that kind of environment variable information can be retrieved using that EC2 metadata API. So instead of hard coding that where my Lambda function is running, the idea is to start leveraging those environment variables. So in this case, for example, the first line shows I'm just using the AWS_region environment variable, which is provisioned by EC2 metadata API. And I'm saying, OK, go figure out which region the Lambda function is running in. That's one. Second is, you can also create your own custom environment variables. In this case, I'm saying S3 bucket. So let's say that is my S3 bucket in my account, and I want to specify where my code is, my files are living, or where my data is living, so you can start specifying those user environment variables. So start leveraging the environment variables exposed not just by EC2 metadata API, but create your own custom environment variables. This also allows you to target your application to different environments. So say test, dev, and prod. So you can start customizing your Lambda functions very easily. We talked about this earlier. It's very important to package your dependencies together in a jar file, as opposed to relying upon the dependencies that are already existing into Lambda runtime. Because if the runtime dependencies are upgraded in the Lambda runtime, we don't want your application to break in any case. So use Maven Shade plugin, for example, which brings in all the dependencies, but make sure you are aware of the limits of the package upload and then the expanded upload. So you don't want to have for example, for the expanded bundle, the limit today is 250 megabytes. So make sure when you take the jar file that was generated by Shade is lesser than that. Here is an example which talks about how do you utilize your memory. The common misconception around Lambda is that, oh, I want to optimize the cost. And the way I'm going to optimize the cost is by using less memory. Now, this was a blog post written by somebody which says they wanted to calculate the prime numbers. So in this case, they are calculating all prime numbers less than 1 million, and they calculated that 1,000 times. Now, it's a CPU-intensive function. And remember, we talked about how Lambda gives you a power dial. So more memory means more CPU, and they're linearly proportional. So if you allocate 128 megabyte memory, you get, let's say, 1 CPU. If you allocate 256 memory, you get 2 CPU. If you allocate 512 memory, you get more CPU. So it's linearly proportional. So in this case, for example, you can see how long it took the compute time particularly for calculating 1,000 prime numbers, 1,000 times all prime numbers less than 1,000,000. So if you look at 128 megabytes, it took about 12 seconds. Cost is about 2 cents. Cost is not the matter here, but if you look at 1 megabyte now, I'm allocating 1 megabyte here. I'm taking about 1.5 seconds, so literally 1/10. I'm sorry? One gigabyte, thank you. So if I'm allocating 1 gigabyte of memory, now I'm only taking about 1.5 seconds, and the cost is still the same. So think about how much improvement that you're getting in terms of a compute time. So very similar cost, actually, as a matter of fact, quite similar. But think about your improvement in the compute time. So make sure you memory right-size your application and have played with that configuration. And if you want to see more details on how to run this benchmark, the details are on the GitHub URL shown over here. There are limits that are defined for Lambda functions. Things like the total number of functions of the upload packages that are sitting in your Lambda console. Yes, there is no cost to it, but there's a limit to it. You cannot exceed more than 75 gigabytes. So the important part is to realize that the total size is limited. So make sure you go through your console and look at the functions that are not into active usage and remove them. All right, let's switch gear. Let's talk a little bit about serverless application model. So Lambda functions are good. I can create one function, I can test it, I can play with it. But my application typically consists of a lot of Lambda functions, and they need to be interacting with the API gateway. How do I define such an application? And that's what serverless application model is. It is defined as a DSL, a domain-specific language, to help you define serverless applications. It is built on top of CloudFormation, which is Amazon's way of deploying or creating AWS resources in a declarative way. So it basically extends CloudFormation and adds 3 more resources over there: functions, APIs, and tables. So functions allows you to create serverless functions, APIs allows you to create API gateways, and tables allows you to very easily create DynamoDB tables. Typically, when you're building an application, those are 3 components that you need for getting your application up and started. Now, in addition to the resources that are created, because it's a CloudFormation template by itself, it supports your usual CloudFormation resources as well. And by the way, this is done in a very open and transparent way, so the specification is all available, and you are welcome to take a look at it and contribute to it. And the URL is shown on the URL at the bottom of the screen. Now let's take a look at it, how a SAM template really looks like. As I said, it's a CloudFormation template, so it's a YAML file essentially. So at the very top, you can see it's a CloudFormation version. Then to the CloudFormation version, you're specifying a transform, saying that, OK, apply this transform to it because I have a few functions. I'm defining a top-level domain, AWS Serverless in this case. And I'm going to define some resources. And those resources ultimately need to be transformed using this transform that is defined over here. And what happens is it takes a look at those resources. Ultimately, it transforms them to the CloudFormation resources. Well, the first thing I'm saying is this is a serverless function. Then, because I'm using SAM here, or serverless application model, I'm a Java developer. I generate my jar files, and those jar files are in my target directory. So I'll talk about SAM local in a second, but essentially, SAM also enables you to test, debug, and play with your Lambda functions locally on your laptop. So in this case, all I'm saying is, here is my target jar file, and point to that. Now, I'm also saying, by the way, I also need a table. So in this case, at the bottom, if you see, I'm saying AWS Serverless simple table. So I just want to generate a simple DynamoDB table, and I'm going to point to that. It's very good to experiment with, but when you are ready, then you can actually substitute this with a DynamoDB table using the regular CloudFormation syntax and be more elaborate and very expressive about it. But it's very easy to get started with. And then finally, I have my API gateway. So in a very declarative way, all I'm saying is type is equal to API, here is my URI, and here is a method. So it'll automatically create all the resources for you that are required for spinning up an API gateway in the backend. So once I have my template, essentially I have two commands. There is a SAM package command, and then there's a SAM deploy command. So the SAM package command, you are pointing to using a code URI to a file on your local machine using, say, target directory. So it'll create a zip file out of it. It'll take the jar file, create a zip file out of it. It'll automatically upload the zip file to a S3 bucket of your choice. Because when you give the SAM package command, you give the S3 bucket location, and it uploads the zip file to the S3 bucket. And then the output of the package command is really another YAML file with the S3 URI kind of replaced over there. So you get a package file or a package template, a YAML file, which is then ready for deployment. And then essentially, then you say SAM deploy. And at that point of time, it's going to take the package template file. It knows where the code is living. It has all the resources defined into it. It'll just deploy and it'll create and deploy all the resources for you. Now, SAM is good. Lambda functions are excellent, but then they're all sitting on the cloud. And how many times do I mean, when you're typically deploying or doing the initial development, you have to do a constant development of your application. And that's where SAM local comes in. Now, what does SAM local give you? Well, SAM local is an extension of SAM itself. It gives you a CLI for local development and testing and debugging of your functions from your favorite IDE. So you can configure it very easily in an IDE of your choice. And then you can start saying, OK, now invoke the function, set up a breakpoint, and go through it and show me what's really happening. So essentially, it uses a Docker image, which is sitting on your local machine. You need Docker as a runtime dependency. It mimics the Lambda runtime for you. The surrounding resources, for example, the DynamoDB database, is still sitting in the cloud. It also gives you the ability by which you can easily provision an API gateway on your local machine. So literally, the API gateway, the Lambda function, those are all being mimicked on your local machine. The logs are all coming over on your machine. So you can start debugging what's really happening. And once you're happy with it, then you can say, take that template file, generate a package template file, and now deploy it into the cloud, ready to roll. And once again, this is done fully in a transparent, open source manner. More than happy to accept PRs, file issues, take a look at it. Amazon.com has the exact same problem that its customer has. Now, in 2014, we were doing 50 million deployments in a year. And Amazon.com is built as hundreds of microservices together. Now, with 50 million deployments, we need to have tools to make sure that we are operating at 36,000 feet, flying at full speed, and changing the engine. Those are the tools that we have used internally for many years to keep Amazon.com up and running. Those are the tools that form the basis for CodeStar suite. Well, the first one was really CodePipeline, which is heavily inspired from our internal tools to generate a deployment pipeline. So CodePipeline was sort of the first tool, and then over a period of time, we built other tools called as CodeBuild, which allows you to serve as a build server. And then we consolidated the tools together, which is sort of in the CodeStar family of suite, which CodeStar, which is running all in the cloud. You can very easily generate a project, like a Java or a Node project. Then it gives you a full capability where you have an IDE in the cloud, which is Cloud9, and I'll show you a demo of that rather quickly. It gives you a full ready-to-go deployment pipeline, no configuration required. It gives you an AWS CLI fully configured. It clones your repo. It has your Git credentials. So everything is ready to go. The biggest point that you want to think about over here is how it does all the undifferentiated heavy lifting for you. As a developer, it wants you to get started. It also deploys all the best practices. Oftentimes, you end up figuring out that, am I using Jenkins? Am I using NetBeans? Am I using Eclipse? How do I plug them together? Where are my Git credentials? How do I do context propagation? It becomes quite a nightmare experience. With CodeStar, I could literally start my project in a few minutes with a deployment pipe ready to go. So let's take a look. So what I'm showing you here is a project that I created this morning. It is a Hello World project, but it is ready to go, essentially. As part of this, what I'm showing you is my dashboard. It shows me my commit history, how I'm using code commit as a backend. So as I'm committing changes to the project, it shows me all the details over there. It shows my application activity, that how anybody is accessing my application. It has a deployment endpoint that is mapped to our API gateway automatically. It shows my deployment pipeline here. And very much like, I can let it trigger by itself, or I can explicitly force a change that, OK, now go make a release here, essentially. OK? Now, I'm in the dashboard here. I can look at my IDE. I can look at my code here. I can do the build. I can do the deployment. I can see the pipeline. I have a fully working development environment for me to be extremely productive. Okay, so let's take a look at my IDE now. Well, this is Cloud 9. This is an IDE which is running absolutely in the cloud, no deployment required at all. Okay, so nothing on your local machine. So now, with this, I have built a very simple Node.js application. Actually, it was part of the template itself. So if I show you here, here is my simple application. All it says is, this is my front-end page of a Node.js application. You created a Node.js web application. Okay? So what I'm going to do is, I'm going to go back here. And I'm going to just change this message here. All right? I'm just going to change the message here. And now I'm going to save this file here. So I go here, File, and I save. Okay? Now, my repo is automatically cloned into my environment. And literally, I just click on a project, one click, CodeStar, pipeline, everything ready for us to go. Now I'm going to say git status. Okay? Okay, that file has changed. So I'm going to add this file here as part of the commit. And then I'm going to make a change here. If I can figure out how to use this keyboard here. Oh, here, no. I thought I figured out where my ticks are. Oh, this one here. All right. Oh. Sorry, guys. Oh, here. There you go. All right. I got it. Yeah. So I'm saying is changing the title here. OK? Commit. And then I'm going to say git push. I push the change here. Now let's go back and look at our CodeStar dashboard here. In a second, you will see how the commit history is updated. And once the commit history is updated, then you'll see my deployment pipeline triggering on the right-hand side. Okay? So if I go back here to code 9, yeah, this has gone through correctly. So if I go back to my CodeStar here, so this should be triggering any minute. Well, there you go. So now it says changing the title. And then on the right side, you can see the change is automatically triggered. By the way, it took me only 5 minutes to create the project, and I'm getting a full template. So the way we see our customers using this is they use CodeStar to create a project, get this entire infrastructure using best practices, all the heavy lifting, and then they have a repo ready to go. And then in the repo, you can start creating your project, start adding your source code. And there are multiple languages that are supported over here. I mean, I don't have enough time to show a lot of details here, but essentially in Cloud 9, again, you can start looking at, say, AWS resources over here, for example, and you can say, show me the remote functions here. So it's showing me the remote functions, OK? Now I have lots of remote functions over here because there are other applications deployed as well. I can right-click on any of the function, and I can say, import this function as a local function now. Now I have the ability to start debugging that function locally. So all of those capabilities exist in Cloud 9 itself, and it's a very powerful tool. So let's take a look at it back here for a second. So my deployment pipeline is going clean over here. Build, deploy. It's going to take a few minutes to build the pipeline and deploy the application again, but you get the point. In a couple of minutes, if I come back to this application and I refresh, it'll just give me the new change over here. All right, I'm going to invite Adrian up on the stage here. Thank you.
Thanks, mate. Do you hear me? Oh, cool. All right. Good afternoon, everyone. So just actually a quick story on why we're talking about monitoring. Monitoring is was kind of left out. In a way, Lambda got really popular. As I say, we started Lambda with S3, expanded a lot, added API Gateway, and people started to add Lambdas everywhere. But what we realized is customers had a lot of trouble debugging applications at scale, especially applications that had dependency with API Gateway, Lambda, and DynamoDB, and things like this. So what we did, we wrote something called AWS X-Ray. And X-Ray is kind of an instrument to debug your application at scale. And it's very easy to integrate. It's similar to monkey patching. You just wrap your X-Ray kind of SDK around the AWS SDK, and then you can start adding traces to everything which happen in your application. And what it does is adds an ID, basically a request ID, to each of the packets that is sent to the application. That means that then you can start debugging. So let me show you a little bit how that happens. So early on today, I deployed some application. I can show you more later, but I deployed simply an application that did some dummy requests, creating users. So there's just a few of those URLs here. You see sign up, and then simply some gets, just to give you an idea of this. And here I have the trace of all the requests that were done in the last 3 hours. Right? So basically, I can start looking at the traces that were very fast, so I don't have too much problems, but I can also see very fast traces that were long. And then I can start debugging into this. Right? So this trace has an ID, and I can see, oh, this actually trace was was a request that was targeting DynamoDB. And then I can say, OK, what took so long? Right? And then I can start debugging here and looking at really what was the exact thing that the request was trying to do. And here it was a put item, basically. Right? So this really gives you an idea of where your application takes time, especially in very large-scale distributed systems. It's very, very useful. Now there's another very interesting thing here. If you put, let's say, in the 3 hours, it's computing the map of all the requests that happened in my region in the last 3 hours. And you see I had 2 applications running, one which is a simple API gateway with Lambda, and I can see basically kind of the response distribution of that application. This is pretty good. It was 100% OK. But you see here, in this application, I started to have some issues. So if, for example, I had 10% errors, right? So I can start drilling into those when I know when things go wrong. And I can see very fast here in my distributed application that, in fact, again, it was a problem with that particular backend, which was the request to put data into DynamoDB. Though this application is made to create issues and so that I can demo, right? So, but it gives you an idea of the things you can build. And in fact, you can build really, really deep traces, right? And if you're interested in understanding a little bit more about cold start and hot start, what Arun said, that when the first time you launch or initialize a Lambda function, we deploy the entire environment, which are containers, Linux containers, with the runtime that you need for your function, and then we deploy the Lambda functions, basically. And this takes a time, right? So for Python, it takes 3, 4, 5 seconds, depending on the size of the package, and Java sometimes 10, 15 seconds, right? So you can see this time exactly here at work. Now, one of the most important architecture that we see with our customers is really event processing. And just to give you an idea of event processing, is really very simple. What we think about event processing is really that an event on A will trigger an event A on B will trigger C, right? So it's really a chain of things, and Lambda is really at the core of it. And in fact, now pretty much the entire environment, AWS environment, start to resonate and work around that. So lots of those services start to talk to each other with those events. And in fact, As Arun said, we started really with S3, and customers started to be very, very imaginative. They had lots of ideas. They thought, oh, but if I put data into my SQS or into DynamoDB or into my Kinesis stream, I want to trigger Lambda functions, right? So now we can support the entire space. But one that is very important and that I want to talk about is the generic kind of event-driven action. And this is very important to understand because it gives you lots of leverage, right? In fact, a few years ago, it was very common for anyone working in the media space to have cron jobs or instance that was doing FFmpeg or this kind of task to extract metadata from images, from photos, resizing, thumbnailing. And to be honest, sometimes it was quite a pain to maintain, right? So it was one of the first, basically, use case of why Lambda came to life. And this is exactly the idea that a customer uploads data into an S3 bucket, and we want to do some compute on that, right, on that object. And the most natural use case is I'm uploading a photo, and I want to resize it, and I want to extract metadata information. I want to use that photo and call artificial intelligence service to extract information from that photos. And in fact, now it's pretty much used by all our customers that have some sort of media pipeline inside. So this is very, very classic use cases. Now, as I said, this use case evolved into something even more interesting. All those customers that started to have events on S3 triggering Lambda thought that, all right, now I have all those Lambda functions that can extract metadata, do resizing, call artificial intelligence services, and then my Lambda function started to become big, and then started to have, go beyond the scope of what we thought of Lambda should be, right? Which should be really the essence of microservices, right? A function that does just one simple thing. So those two things kind of contradicted each other, right? Because people wanted to do a lot of things with Lambda function, but we told them, just don't put everything in one function. So if you just wanted to do an S3, one event, you add a photo into S3 and triggering all those events, customers had to put a lot of logic into orchestrating those Lambda functions. So we listen to the customer, then release step functions. And in fact, step function is exactly that, orchestrating Lambda function. So you can think of it as a state machine running in the cloud that you can control through an API. And it's a very powerful thing. So for example, here I have a workflow that extracts metadata, check the image type. Then if it's a JPEG or if it's an image, a type that is supported by my pipeline, then I will extract the EXIF information and do two things. I will resize, creating thumbnail, and then I will call recognition. Recognition is a service on AWS that you can send an image and do facial analysis, extract objects, scenes, all these kind of things, right? So you just send an image, and we'll return you a set of tags. And this is very useful for customers that have very large media libraries, and they want to index that. So in fact, this workflow is directly extracted from customer use case. And I want to show it to you in real time. So here I have again, it's a Node.js application that is running on my laptop. And what it does is takes a photo, uploads it into S3, and that's it. Then S3 triggers the state machine that we've seen here. So it triggers the state machine, tell it to start, and then the state machine coordinates all the Lambda function to create the thumbnail, call the recognition API, and then store that into DynamoDB and to S3. And then that's it. So it becomes very easy to create very advanced applications. So for example, here, let's say I have an image here that I want to upload. And this now uploading the photo into S3, that's it. Now it triggers a Lambda function, that triggers a step function, that triggers all the different Lambda function, and the execution is even faster at what I can talk. And you see now I have the photo that is extracted directly with the tags. So these are very, very powerful pipelines, right? Because you can start building very powerful application with very a big state machine. Right? You don't have to now orchestrate your Lambda function execution from the client side. You can just upload everything into S3 and start and let the state machine do all the coordination for you. And this is very, very powerful. Another thing that is very interesting, and this I'm going to require your help here, but this is real-time streaming. How many of you have played Clash Royale or Clash of Clans or any of the Supercell game, right? Many of you know Supercell. So Supercell is an avid user of a tool called Kinesis. Kinesis is a real-time streaming service that you can send events to the cloud to be analyzed. And in fact, Supercell sends 45 billion events a day from for their games, right? The entire set of games that they have. Let me repeat, 45 billion events, right? That's a lot of events that you want to process. And they do this because they want to understand what happens in real time in the games. Where are the users spending time? What is hard for a user in the game so that they avoid the user say, oh, that's too hard, I'll never use the game again. So they understand all those events and do some analytics on it. And then fix the game before having users leaving the platform. So it's a very, very powerful service. And in fact, there are 3 flavors or 2 flavors of Kinesis, and I will use one of it today as a demo. But we have Kinesis Stream, which is the raw beast of Kinesis. Basically, is the raw power. So you have a stream where you have to manage a little bit, and then there's Kinesis Firehose, which is the soft flavor of Kinesis where we actually manage part of it. And then there's one in the middle called Kinesis Analytics, and I'll tell a bit more about it later. But what I want to talk about is Kinesis currently. So I always refer to Kinesis as the motorway, right? So when you're on the motorway, there's lines, and each line can take only a certain number of cars, right? If there are more cars in the line, there's going to be a traffic jam. So the only way for you is to create another line on the road, right? So you create 2 lines, then 3 lines. So this is how you augment or you increase the bandwidth in the motorway. In fact, this is the same way for Kinesis, right? So when you want to use Kinesis and send events, you create what we call the shard. That's my line. And the shard is 2 megabytes for read and 1 megabyte for write, so that you can read faster than you can write, so you can eventually empty the stream. And you can have as many shards as you want. So we have customers having tens of thousands of shards, or hundreds of thousands of shards. Now, the beauty of Kinesis is that it's a serverless service. So it's already sitting across 3 availability zones, right? So you have fault tolerance built in from the get-go. So you don't have to do that. So a lot of customers, and I personally have used Kafka, I love Kafka, but it was actually quite difficult to make it multi-AZ, right? You had to do a lot of operations to maintain the state of your stream across multi-AZs, right? Now this is done for you. So it's just easy to start using. Another thing that is important to understand with Kinesis is that it really integrates nicely with Lambda. So in every of the stream or in every of the line that I'm created with Kinesis, I can put a Lambda function that does some compute in real time on top of the stream. So like a road toll, right? The only thing is you don't have to stop. Everything happens really fast. And this is very powerful because now you can send real-time data to the cloud and do some compute on top of it. And this is very important to understand is the Lambda function is executed every second for every shard, right? So if you have 1,000 shards or 10,000 shards, you need to have 10,000 concurrent Lambda function, and by limit 1,000. So remember to increase the soft limit if you start using that. I've seen this with customers, so that's why I'm telling it. But this is nonetheless very, very powerful because you can start doing interesting things. Another interesting thing you can do with Kinesis is what we call Kinesis analytics. That means, and analytics is very simple, is you have your stream, and what you can do is write SQL type of queries on top of your stream, and across the entire set of shards. So you can start doing very powerful real-time analytics on what happens in the entire set of shards, right? So what you do is you create your stream, do your SQL queries, and send the result to another stream, right? So you have kind of your continuous Kinesis analytic pipeline. Very simple. So let's do a demo. Do you have your phone? I'm taking huge risk here. I've never tested this demo with that many people. But if you can go on this URL, you will have just a web page with a quadrant, which you have A, B, C, and D. And we're going to try to see how fast we can do analytics, or what it really means to do real-time streaming and do it live. All right? It sums up when you have the web page. Does it load? How about there, up there? We got? All right, cool. Hopefully we don't crash the app. But this is basically in real time, all what is happening currently. So we have about 230 users. It goes up in real time. So let's do a test. Everyone goes on A right now. It's going to take a couple of seconds. Up. That's cool. Right, so when we talk about real-time analytics, we're not talking about 10 minutes, right? We're talking about 3 seconds here. And if I tell you that all your data is actually going to US East, coming back, being stored into DynamoDB, and then my browser goes and queries DynamoDB in US East, right? So it's big. Yeah, it's not so bad. So just to give it a shot, actually, isn't no one using Windows Phone here? How's that? What happened? Well, you're quite 50-50 on iOS and Android, though. Oh, quite surprised. Majority Android, though. All right, cool. So this is just to give you an idea a little bit of what we mean. But I want to give you the architecture just to show you what it is and how this application is built. This is very simple. When you click on the URL, it goes to an S3 bucket, downloads an index, a web page, which loads some JavaScript libraries. And the JavaScript libraries takes the data of the ball, which quadrant you are, and creates a JSON object with a quadrant A, B, and C, and D. Gives you a unique ID, which is extracted from Cognito, with is service to do authentication, and just send that to Kinesis, right? And I have a Kinesis analytics stream that extracts all this information there, and then does the counting of the number of users, the phones, and all this kind of stuff. Then this is put back to a Kinesis stream. Every of the stream is triggering a Lambda function, which stores the data into DynamoDB. So you kind of realize that from your phone, going through the mobile network, Kinesis stream, analytics, another Kinesis stream, Lambda function triggers, DynamoDB, and then me querying DynamoDB, this was like 3 or 4 seconds. Right? So it is possible to do almost near real-time application, right? So if you have customers and you want to understand what they do in real time, it is possible with the similar architecture. And in fact, this architecture will scale pretty much to any size you want. Right? 45 billion events per day, right? It's quite substantial. And just to give you a little bit, to show you a little bit what it looks like an analytic function, this is my SQL statement that is running on top of on the stream, right? And there's a couple of concepts to understand. I'm not going to go through too much in detail. It's just to give you a teaser a little bit. But you can take the stream, do some operation onto it, and then you can start counting. For example, here you see is very straightforward. I count the entire, the number of users or distinct users across the entire set of shards, right? Now, when you use Kinesis analytics, you have something called a window. Whether you want to use a sliding window or a timing window is up to you. But it's very easy to do some quite simple operation on top of your stream at any scale. On that note, I just want to show you quickly, again, this architecture, because this is quite interesting. And then I want to give you a list of further readings. We don't have that much time to do more demos. I'm doing more demos tomorrow on my IoT talks, but this is all what we could do for now. We've released a lot of different white papers that are very interesting to read if you want to understand more about serverless architectures and the requirements. And on that note, I wish you a good end of afternoon and a good party tonight. Thank you.